Let's take a look at the ghosts of gravity, and this is precise. So we have revolutionary math and real physics that was going on between 1665 and 1998. The first person who was pretty important was Isaac Newton in 1665. He was the one who essentially came up with calculus for the first time almost, and he had this great year when well, there was a plague in London, so he isolated himself in his manor and he started to just do a bunch of math. So he wrote out all these equations. Actually, he was writing more text-based stuff, not really equations. But he saw this apple fall from a tree and basically thought to himself that maybe gravity is the same thing that makes us orbiting around the sun and makes things fall to the earth. Those things must be about the same. So he came up with these three different laws, eventually. The law of inertia, that if you have no forces on an object, then the velocity is constant. And the second law is that just the description of force itself, so F is equal to mass times acceleration. And then he also came up with the idea that two objects basically have equal and opposite forces on each other, which balance out. So he had this little quote that says, "Have not the small particles of bodies certain powers, virtues, or forces by which they act at a distance?" Distance. Forces being acting on a distance. Well, he came up with geometric calculus here. And so he was using this notation where he had fluids, which were the variables. So it would be like x. X is a fluid, something that changes. And then we have the fluxion, which is the rate of change. That would be uh, x dotted, which is essentially the velocity, how that particular value can change. And then we have acceleration, which is the second derivative. So he was making little drawings like this. He was doing geometric calculus more than equations. And he was just writing stuff out in his book, Naturalis Principia Mathematica. So this was how Isaac Newton was able to figure out the area under the curve by doing this type of stuff here and trying to approximate this area. Came up with this unique language, calculus. Well, about the same time, 1684, this guy Gottfried Wilhelm Leibniz was also working on calculus completely separately. But he was doing it more in the mathematical sense, where he had like dy and dx, and he did this little integral sign of f of x and the dx. He came up with the fundamental theory of calculus, so f prime x, and you integrate that, and you get the two endpoints subtracted. And then, so he was kind of looking at this stuff as saying, well, you can do the sum, and the sum can become an integral, boom. So you're just summing up these little boxes, and then all of a sudden it becomes an integral sum, like that. And so here's the area under the curve, essentially, written mathematically. So this was a more mathematical way of approaching calculus, which was a little bit different than Newton's ways, and it was the mathematics that we use today. So this is all the same stuff that we still use. Now, Leibniz has a quote. It says, "Is it reasonable that bodies should act upon one another at a distance through a vacuum without the mediation of anything else?" So we thought that maybe there was something in the vacuum, maybe like an ether or something that would uh, cause forces to propagate. Soon after, we had Alexis Claude Clairaut in 1743. So they realized that Newtonian gravity was slightly off because Halley's comet wasn't really being predicted very well. So this guy Claude Clairaut, he created a perturbation theory version of Newtonian gravity, as you can see here, and that was able to predict Halley's comet much better. It was delayed by Jupiter and Saturn, he says. And so here we have the equation here, and essentially the idea is he was starting to come up with other theories. So like the Earth's rotation makes it a late spheroid. So local gravity varies with latitude. So he was looking at this G, and he was seeing how it was adjusted by the regular 9.81 that we use. And he had like a small adjustment based off the latitude here. And here is the validated three-body problem. So he was looking at how the moon, the sun, and the earth were acting on each other. And he came with this equation right here for that. This is the three-body problem that was validated. So this was Alexis Claude Clairaut in 1743. Next we have, in 1744, Leonhard Euler. He also contributed a little bit to his gravity because he was thinking about how the Euler-Lagrange equation, this equation here, you could minimize functions and figure out essentially the paths of motion. But he also had some other contributions. So he also worked on the complex formula for 2D vector rotations. As you can see, e to the I theta equals cosine theta plus I sine theta. And the magnitude of this e to the I theta is always just 1. So, when you multiply a number by this thing here, it's just the same number again, but slightly rotated by this theta. And here's the graph that might show this. So you have this vector here, which is rotating a little bit, and you have the same magnitude here. This is basically just moving around the imaginary and real axis. He also worked on this 2D Euler topology number stuff. So he was looking at how vertices, edges, and faces have a particular equation that satisfy 2 for these particular ones down here, these polyhedrons. And the tetrahedron, the cube, and the octahedron all have like these different vertices, edges, and faces, but they always have the Euler number equal to 2. So that was another bit of work he was doing. And he also found a couple other integer factorials for the gamma function, the beta function, as we can see right here. So these particular equations are not necessarily relevant to gravity, but they are going to become relevant to other things related to gravity in the future. Let's just keep them in mind, but in general, Euler's contribution to gravity was the Euler-Lagrange equation here. You can minimize the functions. Now, Euler had a quote too, so it says, "Why does the motions of bodies follow laws of maximum and minimum?" That would be this equation right here. A little bit later, in 1800, we had Pierre Simon Laplace that shows up. So he wrote a book too, Mécanique Céleste. And he was looking at how differential equations for Newtonian mechanics works. And he essentially derived this vacuum potential here. Basically, potential of action here would be, but the second derivative is 0. So that was kind of cool. We got this Laplace equation from that. It helps a little bit. But he was also looking at the nebular hypothesis of the solar system formation. So you can see how we start with this like nebula, and over time the nebula starts to swirl around more, and eventually it gathers into little balls. So Pierre Simon Laplace is the one who came up with the idea of the formation of the solar system. So this was kind of cool. And he has a quote too: "Could an intelligence knowing all forces and positions predict the future entirely? You know the positions and all the forces, and you can predict the future." This was Pierre Simon Laplace, 1800. We also have in 1788 Joseph Louis Lagrange. And Lagrange, well, he came up with the Lagrangian, so he was like L equals the kinetic energy minus the potential. And from there, you can basically apply this to anything. So his quote says, "One will find no figures in this work." So he didn't like these types of figures here. Got like a double pendulum here. And so he was able to basically come up with the kinetic energy of the system and then subtract the potential energy of the system. And he could derive momentums and the forces from this. So it's kind of cool. Now, he was also able to realize that you could derive Newtonian mechanics using the vanishing variation of the action from the Euler-Lagrange. So you could say that S equals the integral of the Lagrangian, which is the system here. We have like the kinetic energy minus the potential. And what we want to do is minimize the variation here in terms of time. And when you do that, you get the Euler-Lagrange equation. And you essentially get Newtonian mechanics from that. So here's the momentum and the forces that you can pull out the Lagrangian. So this is crazy, but essentially this was Lagrange doing his stuff, giving us Lagrangian physics. So we had Newtonian physics, and then we had Lagrangian physics, and both of them give us essentially the same thing. Um, but Lagrangian physics is a lot easier than Newtonian physics, so that's nice. And we also have uh, Simon Denis Poisson, Simon Denis Poisson in 1809. He pops up and he's like, all right, well, uh, what if the potential is not zero? What if we have a source potential? So he has the second derivative of the potential being equal to this 4 pi times the density. And this is what the double derivative is. You take the x, second derivative in x, second derivative in y, second derivative in z, sort of add them together. Now he says that the potential might be the negative mass divided by the radius. So we get this g equals negative delta phi term, and that's negative m over r squared. So it kind of looks a little bit like this, where you kind of have like dense stuff here and not very dense stuff here, and all of that contributes to gravity, the whole gravitational potential. So we get the curvature of the potential from mass, charge, or mass or the charge density. It depends whether you're looking at masses or charges. His equation works for both. And he also came up with Poisson distribution because this particular form here has to have some kind of a distribution. But he was doing something more like the K events occur with an average rate of lambda. It's a little equation he also discovered. So Poisson has a quote. It says, "The theory of forces acting at a distance must be founded on the consideration of the distribution of matter." So this was Poisson in 1809. We also have in 1813 Carl Friedrich Gauss. Gauss made Gauss's laws of gravity, electromagnetism, and he also had divergence in the potential field. So here's E dot dA is equal to the enclosed charge over epsilon naught. We also have, so this is essentially just a source charge points out a bunch of arrows. And we also have the B dot dA equals 0. It kind of looks a little bit more like this. If you drew a circle around this, you would notice that whatever is going in is also going out. So that gives us our magnetism, B dot dA equals 0. And we also have the gravity law. So you can see over here, you can draw a circle around gravity G dot dA. And then you get this term, negative 4 pi gm. And so he was able to make Gauss's law of gravity as well. And here's the potential for gravity, the gravitational potential. This was the equation he derived. This was Gauss. He also did the divergence theorem, which is this, that we have the del dot F, when we take the integral over the volume, is equal to the circular integral, a loop, over this area. Now, Gauss says that I do not believe that the nature of space can be determined by reason alone. He doesn't really understand what space is and how on earth we're going to figure out what space is. This is Carl Friedrich Gauss in 1813. In 1834, William Roman Hamilton came and gave us Hamiltonian mechanics. So now we have another way to get the equations of motion. And this has more to do with an equation involving the momentum and the position combined. So we have the kinetic energy plus the potential energy, and taking some derivatives, we can figure out what the gravity is. That's dh over dp. We can figure out what the momentum is, dh over dq. And these equations are a lot more complicated. So you kind of have the equations of flow here, F. As F changes, we have this this bracket here, and then we have derivative in terms of time. It's like the continuity equation or something. But these equations are pretty difficult, but you can see how the graph might look. So you have something that goes in position and in momentum, and it looks like this little swirly thing. This is how Hamilton was able to derive physics again, which is weird, but we sort of had again Newtonian physics, Lagrangian physics, and then Hamiltonian physics, which is a little bit more abstract. But he also derived quaternions, so those are four-dimensional complex numbers. Whereas Euler had derived two-dimensional complex numbers, Hamiltonian expanded them to four dimensions. And so you get rotations in 3D space. So you have real space, and you have sort of this mix of I and J and K. So these are the three imaginary dimensions, I, J, K. And you see that we could square them, they equal -1. Um, so these are some relations he sort of drew out, and you could sort of make rotations in complex space, four-dimensional complex space this time, or 3D space. But yeah, so this is kind of interesting stuff, and all of this is very relevant to future theories of gravity, although in the initial points, it was more just the equations of motion here that were contributing to theories of gravity. So this was Hamilton in 1834, but he also has a quote. It says, "Is there a single function from which all laws of motion may be derived?" So he wants to find one equation that you can get all the motions. And this is in 1834. A little later in 1854, we had Bernard Riemann. Riemann that came up with Riemannian geometry. So he essentially invented the metric curvature tensor. And you could take a little path integral here, the path integral and square it. So like basically a squared equals b squared plus c squared. C squared equals a squared plus b squared. It's like the Pythagorean theorem again. Yeah, so he did a little differential of that. So this is like a little differential area as you're doing the Pythagorean theorem. But if you just have coefficients of 1, then it's the regular flat space. Nothing's weird about it. Of course, these numbers can change, and they can become different and add some curvature to the geometry. But yeah, so we're kind of warping the Pythagorean theorem here a little bit. He also came up with the Riemann hypothesis. So this is kind of some weird stuff. It was basically like there's a zeta function, which is adding up all the numbers from 1 to infinity, or basically this 1 over n to the s. So you can essentially add up all of the numbers, and you're going to figure out what the distribution of primes are using uh, this equation. And he had this issue with the Riemann hypothesis is that there's non-trivial zeros on the critical line of r. The real part is 1/2. So you go s is essentially equal to 1/2 plus some stuff, and all of a sudden you get the Riemann hypothesis. So this is some weird stuff that eventually makes its way into our theories of gravity, but maybe not right now. But anyway, this was some math that he worked on, and he also came up with the second level of Euler characteristic. He started to work on holes. So if x equals 2 minus 2g, you can see how geometry starts to look a little bit weird if you have that kind of stuff going on. You know, like these genuses, which are holes. A hole of 0 is a sphere, hole of 1 is a donut, hole of 2 is a multi-hole donut. So this has two holes in it. See, it's like a figure 8. And so Riemann was working on curvature and these different geometries and prime numbers. So here's a quote. It says, "Is it quite conceivable that the geometry of space is different from that assumed in Euclidean geometry?" So this is just regular Euclidean geometry, but he thinks that space might be different than what we think is regular geometry. This is 1854, Bernard Riemann. We come to James Clerk Maxwell in 1865. And he came up with the finalized Maxwell equations. So we already have Gauss's law of electricity, which is this one right here. Del dot E equals the charge density over epsilon naught. You can also do integral form, E dot dA equals Q enclosed over epsilon naught. He came up with Gauss's law for he had Gauss's law for magnetism here, so we had del dot B equals 0 and E dot dA equals 0. And these are both from Gauss. And then we also have Faraday's law, which is del cross E equals a changing magnetic field. And that's also written as E dot dl. See here, we're changing the magnetic field over the area. So this is Faraday's law. Essentially shows you how magnetic field changing creates an electric field. And then we have Ampere-Maxwell law, which Maxwell he added this little term right here that says that a changing electric field generates a magnetic field. So this was done in 1865. He unified all four of the electromagnetic equations. And we finally had a complete unified theory for the first time. That's kind of interesting. The problem is that these theories were breaking Galilean relativity. So if you make a little translation in space, x prime equals x, and you move a little bit, then all of a sudden these equations don't work anymore, and you get different equations after translation. So we knew that something was wrong with our description of space, which in that time was just Galilean relativity. As you could see, we just take, we just add the velocity to the position linearly. So Maxwell had a quote too. It says, "Is gravitation due to the action of a medium?" You might think that again, the medium has something to do with the gravity, just like it did in electromagnetism. With all these changing things back and forth. And here is a parallel plate capacitor right here. You see that there's two big plates. The electric field goes straight across, and then this B field does this little rotation around it, as you have this current that goes into it and charges it. It charges a Q and minus Q on both sides. So this was James Maxwell in 1865 coming up with the unification of Maxwell's equations. So now we come to 1869. We have this guy, Elwin Bruno Christoffel. This guy right here. So he came up with the Christoffel symbols. And these are essentially just derivatives of the metric tensor. So we have g here again, and we're just taking some partial derivatives. And so we get the sum of those, and it's this little symbol right here. And we have to take control of like different space directions. So that's why we have all these indices here. We're trying to track how we're taking derivatives, cross derivatives, in all the different dimensions. It's just kind of a big complex derivative right here. But he's also looking at how basis vectors twist and stretch. So if we look down here, this picture, you see how we could have a straight geometry, and a straight grid has straight lines. If you twist it a little bit, well, the vectors also twist. And if you twist it even more and curve it, then all of a sudden these vectors have a little bit of curvature. So the basis vectors of these spaces twist and stretch if there's curvature. And so he asked himself this quote, "How do quantities change when the coordinate system itself varies?" This is the coordinate system varying, and how do quantities change? So he came up with the covariant derivative, where he's comparing vectors, nearby points. So we're basically looking at these two vectors, and we're basically looking at 2 points and comparing them. It's this weird little equation here. And it leads to the geodesic equation here. So we have the straightest path allowed by geometry. As you can see, we go A to B, and we have to travel along this weird curved path. So this is the equation that defines that. Second derivative position, we have the Christoffel symbol, and then we have position moving around. And so you just go from A to B, and there you go. It's the geodesic equation. We came up with these Christoffel symbols and the geodesic equation, how to navigate through curved spacetimes. Just spaces, not necessarily spacetimes yet. Just curved geometry, how to navigate through curved geometry. This was Elwin Bruno Christoffel in 1869. In 1889, we had Gregorio Ricci-Curbastro, and he shows up, and he's like, well, let's do some tensor calculus. He came up with the Ricci tensor, so he was able to take the Riemann curvature tensor that basically puts curvature together, and he contracted it. So this is the Riemann curvature tensor here with the K, and And he's just like, all right, well, let's just contract it. We'll get it with average curvature is just R, or IJ, really. And then you could take, so this is the trace of the Riemann curvature tensor. You're basically doing an operation to get this. And then you could take the trace of the Ricci tensor, which is this, and you can get yourself the Ricci scalar. Now, the trace means that you're just adding the diagonal components, okay? So the trace isn't a very complicated procedure, but you just start adding up the diagonal components, um, and then all of a sudden you get the Ricci scalar, you get the Ricci tensor, and Ricci scalar. So this is how he started to quantify curvature, basically give it a value that you could measure. And he also looked at how you could use Taylor expansions to figure out what the area and volume was for curved spaces. So you have a flat space, you have like an area like this, and if you put it on a curved space, all of a sudden the area does some weird stuff and it warps itself. So you can have this Taylor expansion, which gives some corrections for the curvature. So Ricci, I suppose, he was able to figure out how things are affected by curvature around geometries. And we have this quantification of that curvature. And he says, there's this quote, which differential expressions remain invariant under transformation? So he wants to know differential equations, essentially. Now, in 1896, Tullio Levi-Civita pops up, and he wants to do a double covariant derivative of the vector field here, and that leads to curvature. So you can see how this term right here, you can take a double covariant derivative of the vector field, and that leads to this curvature term here. That's the Riemann curvature tensor. So he shows how you can expand this commutator that's operating on this vector field. And when you do the expansion, you cancel out all some terms. You basically get this massive thing here. So you get the partial derivatives of the Christoffel symbols, and then you get some Christoffel squared symbols here. So we're just doing lots of double derivatives here, the second derivatives. Well, he wants to know sort of the difference between two paths. Here's how you could take two paths around this sphere, and you have the vectors that point and start curving and curving and curving. This one ends up pointing this way, but if you go this way and you end up at the same point, all of a sudden you're pointing that way. So these two vectors have this difference, and they end up at the same point here. And the failure to commute is the curvature. So he was able to essentially calculate curvature from two vectors pointing in different directions and the difference between those two vectors and how they point and stuff. So Tullio's Levi-Civita's quote is, "What is the true meaning of parallelism in curved space?" So here are parallel transported vectors in curved space. This was in 1896. In 1904, Hendrik Lorentz shows up, and he comes up with the Lorentz transformations. So he was looking at electromagnetism, and he was like, well, remember, the Galilean relativity doesn't work here. So we have to do a little adjustment. We have to do t prime equals gamma times t minus vx over c squared. And then we have x prime equals gamma and then x minus vt. So this is a slight change to the Galilean relativity by this gamma term. This gamma term is equal to 1 divided by the square root of 1 minus v squared over c squared. This essentially forces c squared to be essentially the limit of velocity that you can be moving at. So he kind of set a limit in terms of the speed of light, as fast as you can go. And it sort of makes the transformation, the coordinate transformations as you're moving, just a little bit different than the regular x minus vt. He also realized that this has some implications. It has implications of time dilation and length contraction if you're moving fast. And this is the way he was thinking about it. He was like, well, if you're moving, your clock ticks slower, and if you're moving, you're faster to the speed of light or so, you become flatter. So this was his interpretation of time dilation and length contraction, is that it was very literal. fact that clocks tick slower, like literally tick slower. And they don't literally tick slower, they both tick at the same speed. They're both clocks that tick at 1 second. But because if you're both in your own frame, you look at your own clock, you're not going to notice any difference. So for you, your own clock ticks at your constant speed and it's never going to change, no matter what velocity you're going. But to somebody watching, that's where the time dilation happens. That person is going to see your clock ticking slower. You're going to see your clock ticking at the same speed. But somebody else that sees you moving, they're going to see your clock ticking slower. So that is what time dilation is, although he thought it was literally clocks ticking slower. And also literally with the movement, he thought that you would literally shrink as you move faster. But that's not the case. You're not literally shrinking. You do not notice yourself shrinking. Somebody else watching you sees you shrink. That's just a trick, an illusion. So, Lorentz says, why do all experiments give the same result regardless of Earth's motion? And he doesn't really see why everything has got to be so invariant. It doesn't matter what's going on with the Earth. Everything's always the same. All the equations always work. It's so strange. But anyway, this was 1904. In 1905, we have Albert Einstein who shows up. Now, he has a great year, the Annus Mirabilis. So the first thing he figured out is the photoelectric effect, that the energy is equal to h times the frequency. It's Planck's constant times the frequency. So basically, as some light rays smack a surface, it kicks out these electrons and they start moving at a particular velocity with kinetic energy. Um, he also discovered Brownian motion, so how things sort of wiggle around in weird ways. And they basically in a cup, if you look at the molecules, they'll be moving around in very random ways. They're not standing still. And he also explained special relativity in terms of uh, mass energy equivalence and how you have E equals mc squared. So the first year, Omnus Mirabilis of Einstein, he just explains some simple concepts. He shows how the coordinates change as you move very, very quickly, and how you're keeping all of the coordinates invariant as you move through special relativity. Um, so his quote is there an experimental difference between acceleration and gravitation? He was already looking at how gravity and acceleration have some sort of a relationship. So this was Albert Einstein in 1905. In 1908, Hermann Minkowski, he was Einstein's teacher actually, and he came up with the coordinates that are space-time coordinates. So he has ct, x, y, z. Time has to be multiplied by the speed of light, and this is a 4-vector. So he has space-time coordinates which form an invariant interval. So instead of the regular old c squared equals a squared plus b squared, we have this equation where the length is equal to the negative time squared. And then we have the positive space. We have this negative 1, 1, 1, 1, which denotes this in flat spacetime. And this was based on coordinates. Now he also drew geometric light cones, so spacetime diagrams for the relativistic Lorentz transformations. That would be this type of stuff here. We have past light cone, the future light cone, and basically it makes this little cone as we go forward in time. Because light's always expanding in all directions at a very specific constant speed. Um, and he also figured out the Lorentz group, which is how you do rotations and boosts through this geometry right here. And this geometry is actually popping out in 3D at us. So this thing, as it starts to angle itself inward, it's also rotating itself outward towards us. So that's kind of crazy, because otherwise this thing wouldn't be flat. But it's flat in terms of its own perspective. So this was in 1908, Minkowski's. His quote was, "Henceforth space by itself and time by itself are doomed to fade away." And that's because you have to have time and space together. You can't separate them. This was in 1908. Well, David Hilbert pops up in 1915. So he's asking himself, can the equations of physics be derived from a variational principle? So he derives the Einstein-Hilbert action. He comes up with this variation here. You take this curvature r, multiply it by the negative trace of the metric tensor, and then this is a four-dimensional integral, so it's a space-time integral in four dimensions. And if you take the variation of that and set it equal to 0, what that means is you're going from here to there, and these little lines that swirl around it all equal 0, and all you get is a straight line from here to there. From that, he was able to derive this basic form of gravitational field equations. So we have like the Ricci tensor minus metric tensor times the Ricci scalar equals the stress energy tensor here times some constant, hey, the coupling constant. So you essentially derive an equation for gravitational fields right here, which was quite interesting. However, in 1915, Albert Einstein found what K was. As you can see, he calculated K to be 8 pi g divided by c squared. So this is the coefficient that goes in front of the stress energy tensor. And he also went ahead and added this term here, the cosmological constant term that has to make this work properly. Otherwise, the equations don't necessarily work. We have, again, the Ricci tensor minus the Ricci scalar times the metric tensor, and adjusted by this term here gives us the stress energy tensor. So we basically have this form here of general relativity where things are curved and space is curved, and that's what keeps things rolling around the surface here. The problem is that general relativity, space-time curvature causes gravity. It's incompatible with quantum mechanics. The math just doesn't work with itself. There's two languages, although we haven't discussed quantum mechanics yet. But it also doesn't explain dark matter. We haven't discussed dark matter yet. What is this? But it also leads to singularities and black holes in the Big Bang. We don't really know what black holes are right now. But the idea is that general relativity was incomplete at this time. It seemed correct because what we were doing was he was looking for like a solar eclipse or something of, I think, Mercury. I'm not exactly sure, but he was looking at some eclipse and he realized that it would appear here because the curvature of the planet would cause the light to appear here rather than appearing here. So this was how he was able to again predict one of these, you know, astronomical events that made it clear that his equations were correct. He was able to predict one of those eclipses, one of those positions in the position of Mercury, I think it was. So that's very interesting. And so this was general relativity. And you can see Einstein here drawing his R's. And he asks, how are the laws of nature to be expressed so that they are independent of the choice of coordinates? This is Albert Einstein in 1915. So important, general relativity. These equations are solid, have been tested against, and they're absolutely true. They just have a couple of small issues. So we're not yet at the full theory of gravity yet. Yes, we have to keep going. Well, soon after, 1916, Karl Schwarzschild says, I have succeeded in finding an exact solution to Einstein's equations. Now, he was a little bit crazy because he was an artillery officer in World War I on the Russian front. So he was just calculating ballistic trajectories. So that was why he was so good at this sort of. He was already kind of doing the same type of stuff. We're calculating projection trajectories of, objects as we're going through space. So, he basically quickly came up with the Schwarzschild solution. So he assumed a spherically symmetric vacuum solution, and he realized that there was this strange critical radius on the boundary. So first he saw that curvature is equal to 0. And then he was looking at how he could take A and this B, these constants, set them basically, multiply them together in 1. And then he said that A must be 1 minus 2 GM over R. He plugged it into the path interval here, ds squared. This is again, we're looking at c squared equals a squared plus b squared. And then he came up with, he just basically plugged in those values, and out pops this right here. This is the Schwarzschild metric. And it basically just describes this curvature, this curved sphere here, where there's this sort of this issue happening at r equals 0, because r equals 0 down here in the denominator would cause some problems. And then we have the Schwarzschild radius is a very specific radius, 2gm over c squared. Okay. So this was some mathematical solutions to Einstein's equations in 1916 by Schwarzschild. Well, in 1933, Fritz Zwicky starts to notice some interesting stuff. He notices that several galaxies were orbiting too fast in the Coma cluster. Here's the Coma cluster right here. Here are the galaxies within it. They're all orbiting each other in a sort of way. But he noticed that they were just going too fast. So here's the orbital velocity, which is approximately gm divided by r. And here is the equations he was looking at. So he was like, basically, okay, we can figure out what the scene mass is by using this equation. M over L, this is basically solar mass divided by solar luminosity. It's just a little ratio. And then we multiply it by the luminosity of these galaxies. And then you get something like this, 1.8 times 10 to the 13 kilograms. And well, the problem is that these velocities are not enough to explain the orbital velocity. It was too high, so the total must be greater than what was seen, because the velocity is too high, as there's missing mass. So unseen mass would explain this higher velocity. So we can make this little equation here. Let's just call it v squared r divided by g, and then all of a sudden we get this, because you're solving for m, and we get this ratio where we get 25.6 times more unseen mass than there is seen mass. So that's just like a huge amount more dark matter than there is normal matter. And Zwicky's quote here is, if this would be confirmed, that we get the surprising result that dark matter is present in much greater amount than luminous matter. This is the first dark matter evidence, but nobody really took too much attention to it. It's just kind of this strange calculation he made. Well, in 1936, Friedmann-Lemaitre-Robertson-Walker got together. These people right here, and they came up with the this metric right here that figures in the scale factor, which would be the expansion of the universe. And I started to think, okay, maybe there's curvature of space, could be flat, closed, or open, 0, +1, or -1. And these are the types of consequences. Here's positive curvature, here's negative curvature, here's flat curvature. And this could be applied to, space. And I think we've figured out that space is essentially flat in all directions. K equals 0. So that's fine. But that leads us to the Friedmann equation. So he was able to calculate the expansion and evolution of the universe based off of the Hubble parameter h. So h squared equals a dot divided by a squared. And then we get this 8 pi g over 3 times density minus k over a squared plus the lambda over 3. And so, well, this just basically describes the expansion and evolution of the universe. And we get this kind of formation here. The universe must have been expanding over time. So here's some quotes from Friedmann-Lemaitre-Robertson and Walker. Friedmann says, "The curvature of space may be a function of time." Curvature of space may be a function of time. Lemaitre says, "The evolution of the world can be compared to a display of fireworks that has just ended." It's interesting. And Robertson says, "The large-scale structure of the universe is determined by symmetry." And Walker says, "The assumption of spatial uniformity leads uniquely to a simple form, the metric." So in 1939, Oppenheimer and Snyder did some calculations, and they calculated about black holes. So they looked at critically massive stars, and they realized that if there's no pressure, no rotation, and it's spherical, then it could collapse to a zero radius. So here are the equations of that, where you have the radius, r dot divided by r squared equals this terms right here. If we rearrange for that, um, and we look at this, some equations here, we do some calculations, we realize that we can take r to 0 in finite time. And this describes how r changes, and then this describes the time integral for how we could take r going from the initial to a 0, and we get a finite time. So that's interesting. Oppenheimer and Slimer essentially prove that black holes exist and how the radius just implodes. And in reality, it looks a little bit more like this, where we have an object, and then all these gases start to expand outward, but the inner core implodes inward. So you get basically a black hole immediately, and all this stuff spitting out from it. That's just dust. Uh, all the matter inside has been collapsed to 0. This was in 1939, Oppenheimer and Snyder. Now, in 1955, Amal Kumar Raichaudhuri, he was looking at world lines and these light cones here. So he came up with the Raichaudhuri equation, which says, basically, first of all, let's realize that this theta is not an angle. But he's looking at the cross-section rate of change of this angle. So here's a cross-section, and we're looking at how this cross-section area changes. You can look at the cross volume of world lines, or you could look at the cross area of a light cone. So this is a light cone, and if you cross it, it could become flat, or it could be sheared. It's an ellipse. You can see here the two images. Now, this is how you can get from the rate of change due to the volumes with world lines, and this is the rate of change due to the areas. This is for null expansions, just a light cone essentially. So it's based off of the shear distortion, vorticity, rotation, and your curvature R. So this is some interesting equations that was derived by Raichaudhuri, how you could take these slices of light cones. Interesting. This was in 1955, and he was saying to himself, under what conditions do world lines focus? In 1965, we reached this discovery of the cosmic microwave background. So Penzias, Wilson, Dick, and Peebles, these guys right here, they discovered the cosmic microwave background because they were looking at radio noise in all directions. And they calculated the temperature to be essentially 3 Kelvin. Well, that was an important observation there. This was an observed number because these two people right here, Penzias and Wilson, they they discovered this. These two people right here, Penzias and Wilson, made the observation that there was a 3K blackbody temperature of this radiation. But Dick and Peebles over here, they made the calculation math sometime earlier using a decoupling redshift and the photon baryon decoupling temperature. They made some calculations here and they realized that um, you would have this 2.7 Kelvin temperature if there was some sort of a light photon field you decouple it. So this is some crazy stuff, but the idea is that they came up with the discovery that there was this massive field of light much time after the creation of the universe that was sort of sitting out there, frozen in time. And here's some quotes. So Penzias says, "We found an excess antenna temperature, independent of direction, season, or time of day." Wilson says, "We were unable to get rid of this background noise no matter where we pointed the antenna." Dick says, "Well, boys, we've been scooped." Peebles says, "If the universe was once hot and dense, there should still be background radiation." They had made the calculations that if the universe was hot and dense at some point, then there would be a background radiation. It's the cosmic microwave background. This was in 1965. There's two different teams. Now, in 1970, Vera Rubin and Kent Ford, um, this is one of the first women that we have come across, but they discovered more dark matter evidence. So they brought back dark matter from the 1933. They realized they were looking at thousands of flat galaxy rotation curves. So here are the galaxy rotation curves that, for some reason, the expected way would be going like this, going down with the radius. We would expect that the velocity should decrease as the radius goes out. You can see 1 over r drop off of velocity is expected. Boom. But these velocities were flat, as you can see. So the measured velocity was a lot higher than what was calculated. So this was some very strange uh, evidence that could really only be explained. Well, it couldn't be explained by visible matter. So this basically was a final conclusion that in 1933, the evidence of dark matter, combined with this evidence, that they have thousands of rotation curves. This is where we started to realize dark matter is definitely out there because it's really affecting the velocities of these galaxies that are rotating. They're just rotating around too fast. The mass out here should be getting thrown out if they're going that fast, but it's not. So Vera Rubin says rotation curves of spiral galaxies do not decline, they remain flat. And Kent Ford says the data was reliable, the velocities were real. This was in 1970. 10 years later, in 1980, Alan Guth shows up, and he's still alive. Um, yeah, I think he goes to, he worked at MIT for a while. But he came up with the idea of inflation. So without inflation, you would have this model right here, the Big Bang. But with inflation, it would be something more like this. And so it started very, very small at a point, and then expanded greatly in a very short period of time. So you get this massive ballooning happening. And this was his idea of inflation. So we have this false vacuum state where pressure is equal to negative density. And so you basically get, uh, you basically want this idea that if you want a positive acceleration, then this equation must be negative. And so we have, he essentially said there's an exponential scale factor, uh, A, which is e to the ht, and here is h. This was how he was able to basically show that you have an accelerated expansion because you have an exponential scale factor. So this was inflation at the very, very start of the Big Bang expansion of the universe model. This is 1980, Alan Guth. And he says, inflation proposes that the universe underwent a period of extremely rapid expansion very early in its history. This was in 1980. So then we have 1984, where we finalize the model for dark matter. This group right here, Blumenthal-Faber-Primack-Rees, Blumenthal says the cold dark matter theory predicts a hierarchical clustering of matter with small objects forming first. We have small halos, then we have galaxies, and then we have cluster. And Faber, I'll use another woman here, says the mass to light ratios of galaxies increase with radius, implying that light does not trace mass. So that means that it's EM decoupled. And we'll get into this stuff. So non-baryonic is what they sort of, the first condition here. That's what cold dark matter is non-baryonic. The reason is because basically have this density ratio here. And then we're looking at the observed baryon ratio, it's 0.02. And then we have this calculated theoretical 0.14, which is what we calculate for the strength of gravity. And that means that there's a discrepancy between this. The baryonic mass cannot account for all the gravity. And so there's some missing matter, which we call dark matter, which is equal to the total minus the observed. And so we have this 0.12 left over dark matter that's non-baryonic. We've determined it's non-baryonic because it can't account for the effects of gravity. We've already counted all the baryons. So there's just too much gravity for the baryons that exist. So cold dark matter is non-baryonic. What does that mean? It's not a regular matter particle. It's non-relativistic. So that means it's cold, which means it's very slow. It doesn't move fast. The way we can prove that is essentially looking at this term here, which is the density of at a point minus the average density divided by the average density. So we're looking at sort of formation, or sorry, we're looking at the this density term here. Now, if d equals 0, then it's just average density. If d is greater than 0, then we have overdense region, and if d is less than 0, we have underdense regions. But formations only form when overdensity, that's d is greater than 0, is growing. So we have to have a change of the overdensity. And, well, notice that we have a formation velocity. So in order for stuff to form, it has to move at a certain rate. And so here's the equation for formation velocities, or sorry, how we can grow over density. It should include this term right here, but we are going to assume that this term is equal to 0, and therefore the velocities are, this velocity squared term essentially equals 0, and so then we basically conclude that in order for the matter to, structures to form, this equation right here, we have to have very slow dark matter. Then we can also examine the velocity itself. So regular baryonic matter has this particular equation in terms of formation velocity, which includes the pressure term, and it includes the EM coupling term. But for dark matter, we realize that we have pressure equals 0, and the coupling term equals 0, or approximately 0. So the equation for dark matter is a lot simpler. And with that, we're able to essentially get these two types of um, dark matters here. One is cold dark matter. You can see it has a lot more filaments and is a lot slower, so it doesn't clump that much. The warm dark matter is a little faster, and as you can see, the clumping is happening more, so just get less of it, less sparse. It's a lot more clump. Cold dark matter is a lot less sparse, a lot more sparse. So basically, these are how we can show that cold dark matter is cold, non-baryonic, non-relativistic, and decoupled from electromagnetism. Primack over here says cold dark matter provides a successful framework for understanding the formation of galaxies and large-scale structure. And Rees says most of the matter in the universe is dark, but cannot be detected by its radiation, only by its gravitational effects. So this was how we sort of finalized, in general, the one of the first theories of cold dark matter in 1984. This group right here. And finally, in 1998, we have these three members here, Perlmutter, Schmidt, and Rees, where they basically realized that there was something called dark energy. Because they were looking at the expansion, the velocities, or they were looking at the redshifts of supernovae, distant supernovae. The supernovae were too far, they were too dim, so it just ordinary matter couldn't account for this greater distance than was seen on the telescopes, because ordinary matter has positive density and pressure, and in order to get an accelerating expansion rate, this is the only thing that could explain the velocities moving so fast, the supernova are so distant, is they required an accelerating expansion rate. So in order to do that, we have to take the scale factor, or the Friedmann formulas here, and we want a positive A double prime, which means that this term on the right here has to be negative. In order to do that, we have to have a negative pressure. But nothing's going to have a negative pressure as not ordinary. So if we have a cosmological constant, or a dark energy term, then we can divide the pressure by the density, and we can get -1, this ratio between them. So the pressure is equal to the negative density. This is what a cosmological constant essentially does, is it gives us a negative energy term, or negative density term, negative pressure term, negative density term, both of them. So now we essentially get this dark matter. This would be dark energy. That would explain an accelerating expansion rate. And we haven't really observed dark energy, but this would explain it if we had a cosmological constant. So Perlmutter says the simplest explanation is a cosmological constant that would cause an accelerating expansion rate. Now Schmidt says we thought we were measuring how much the universe was slowing down, and Rees says we did not set out to find a new component of the universe. But as we can see on this graph right here, it says the accelerating universe is here. So we have non-accelerating universe is this line. This would be a straight line. But as you can see, the supernova data was way, way above the line. So clearly we have to have an accelerating universe for this to happen. So that essentially concludes our precise measurements of gravity, dark matter, and dark energy, covered black holes, covered all the normal things that would basically lead to a complete theory of gravity. Although there are still several things that are missing from our theories, so we might have to continue this further. But for now, this is essentially what is known, and there's not really much more that we can get from all this gravity stuff. not many more real evidence that we can find. This is all evidence. Anything further from here is just going to be theoretical and isn't going to be quite as accurate. But that's the way it is. Anyway, thank you so much for watching, and hopefully